Alright, so today I'm going to be talking about power series, the differentiation of power series, the integration of power series, and particularly geometric power series. A lot of stuff's happening in lesson 7-4. It should go without saying, 7-4 is a very important lesson. 7-5, 7-6 form a trinity of hugely important topics in BC. If you can understand every word of 7-4, 7-5, and 7-6, you are guaranteed to get 1 out of 6 questions on the FRQ completely right. It's always 1 out of 6 questions on the FRQ, with maybe some sprinkling of stuff from chapter 8. So, get ready. I was waiting for that for like 10 minutes before I started recording, just to hope the computer booted up, and I'm sorry those terminal windows keep popping up. I don't know. Whatever. Triggered. Okay. So, if you watched the 7-3 video, which you really should have before you watch this, you will remember that a geometric series was a sum of a times r to the n, where r is some constant. And we learned that if you add all these things up from 0 to infinity, what you get is a over 1 minus r. So you get a constant. If you add up a bunch of constants, you get a constant. So the idea is that we could do the same thing, except instead of a constant, we could make it a variable. A plus a times x plus a times x squared. I mean, I guess I should write that out too. Like, this is a plus a times r. That's what that sigma notation means. I know some of you might be struggling with sigma notation. There you go. That's what that means. That's what that sigma notation means. So this is a power series. It's a series where there's x. That's all it means. A power series is a series that has x in it. Okay, why is it called a power series? Because it will have powers of x. If it's a series, it should have powers of x in it somewhere. Okay? This series is called a geometric power series. Why is it geometric? Think about it. 3, 2, 1. Because each term is a multiple of the last. To get from a previous term to the next term, I multiply by x. I multiply by x. And so on and so on. If it converges, what must be true about the variable x? What must be true about x is that its absolute value had to be less than 1. And in case you got bad at this, or that you're not good at this anymore, we have to have that relationship. That's what this means. If the absolute value is less than 1, we can get rid of absolute value by splitting it like that. Why must that be true? Why does that have to be true for this to converge? Because the GST says that geometric series only converge when r is less than 1. The absolute value of r is less than 1. So if r is x, it's a GS with r equal x. So we need the absolute value of x to be less than 1. Pause that. Make sure, go back and rewatch it. Make sure that whole opening makes sense. So now, if it converges, then we're equal to the first term. Then I'm equal to the first term divided by 1 minus r. So, what did we just show? For x values in this range, in this interval, this function is this series. Not approximately, is. They are the same thing. And that is a very powerful technique. It will seem not that powerful. We'll have a special presentation before 7.5 about why this is so important. But this is a whole game. This is why it's part of calculus. Because I can turn this function into a series, and I can turn the series into a function. In general, as a preview, this is hugely important because it will allow us to approximate functions using polynomials. And why are polynomials so nice? Polynomials are basic arithmetic. Take 1 plus some number plus that number squared. That's easy to calculate. What's hard to calculate? Natural log, e, sine, cosine, crazy banana functions. Okay, so that's the preview technique. We want to find a way to write a function as a series. And here we go with doing that. I gave myself more space than you have. I want to make sure we talk about this. So the name of the game for this and the next 4 examples is I want something that looks like this. Because I know what that series is. I know that series is a plus ar plus ar squared, and so on. And I also know that series is that series. So I want to get this into that. Okay? So I'm going to say this would be a geometric series like that. A equal R. Oh, sorry. A equals 1, the top. And so I knew plus x. I want plus x to equal minus r. That's one way of thinking about it. So I want r would be minus x. If that doesn't make sense to you, because I want it to be minus r over here, another way that some students like, set the bottom equal to the bottom you want it to be. We're trying to find r here. Solve for r. X equals negative r, and now we're back to that step. R equals negative x. Okay? So I'm going to use either one of these methods. This is more common. I would say this is the more appropriate method in more cases. You'll see why. So this is a geometric series with a equals 1 and r equals negative x. So I would say, oh, f of x is a plus negative x. A times negative x plus a times negative x squared. I'll write it with colors in a second in case that'll help you. Plus, now the standard way they want you to do 4 terms and the general term. That's the directions every single year on the AP test. So 4 terms, 4 non-zero terms, dot, 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 and the general term. R to the n. So in case it's helping you, in case this helps, 1 times that, 1 times that, it's still a times r. And in case you're not seeing it, this is r. R to the 1, r to the square, r to the cube, r to the n. Now I'm going to simplify that a bit just so you can see what's going on. What we have here is, if I take off the powers, what I have here is this nice series. 1 minus x plus x squared, negative squared, minus x cubed. 4 terms, and dot, 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 the general term. So usually we separate this out. A lot of students seem to have trouble with exponent rules. If you aren't good with your exponent rules, you will have a really bad time. I can distribute exponents over multiplication like that. So I have negative 1 to the m with parentheses, x to the m. This form's important because this is what we would call an alternator. And you'll see why those are so important. This makes it an alternating series. It alternates from positive to negative to positive to negative. Okay? And so since I wrote out the general term, as soon as you realize the pattern for the general term, you can also give the series using sigma notation. So the sigma notation from n equals 0 to infinity is the general term. Now, writing it this way is helpful for a variety of reasons. If you had a hard time with that exponent thing, you could have also written it this way. You want to make sure you start at 0 and go to infinity in most cases. This is a much more preferable answer because it highlights the fact that the series is alternating. You will see that this is much more preferable as you move through Unit 7 and 8. It also asks me for, and I know this problem asks you for a lot, the interval of convergence. The interval of convergence, that would be this part here. I want to set the absolute value of r, the interval of convergence. We want the absolute value of r less than 1. What's r in this case? R is negative x. So I want absolute value of negative x to be less than 1. The absolute value of negative x is positive x. It's absolute value of positive x. So I have the interval of convergence. And that's what I would call the IOC, the interval of convergence. And now I did all the things this series wanted me to do. I would suggest you watch the next 3 examples, and then if it's still confusing, go back. A lot of students in BC this year didn't like this. It's not that bad. Alright, so again, the goal, I'll just keep putting the goal over here. We want something that looks like a over 1 minus r. So usually the top's going to be a. Easy peasy. Right? I just set the top to be a. Usually. There's some tricky stuff that happens. And then I make 1 minus r equal 1 minus 2x. Now, maybe some of you already know what's going to happen. That's okay. Sometimes it gets a little trickier. If you solve for r, negative r equals, I subtracted 1 from both sides, and r equals 2x, okay? So we have those 2 bits. So g of x, a plus a times r plus a times r squared plus a times r cubed plus dot 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 plus a times r to the n plus dot dot dot. I cannot emphasize enough, without this you will lose points. Why? Because g of x is not equal to anything else. It needs to have every single term, infinitely many terms. Alright, let's simplify it, see if we can't find the pattern. And again, you could be done there depending on how you're feeling about life. That sounded weird. Depending on how you feel about all of this. 24? How could you simplify this? If you said 3 times 2 to the n times x to the n, great. Now in general, that's not as necessary, okay? In general, for this one, that's much cleaner. Why do I want to separate it out here? Because again, the negative 1 to the n is a very powerful idea. 2 to the n, not so much. So I'm going to write this in sigma notation from n equals 0 to infinity as 3 times 2x to the n. There's my sigma notation. 4 terms in the general term. Okay, again, or I don't really want you thinking about this. But also, this would be acceptable, right? We'd also accept this. Don't get confused. Just do whatever's easiest for you. I know most people prefer that. I'm not surprised. All right, interval of convergence. We want the absolute value of r to be less than 1. R in this case is 2x less than 1. How do I get rid of absolute value? I bust it out. I don't know. The way I tell my Math 1 students is to break 2x out of the absolute value jail, I need to warp reality so that there's now 2 versions of the 1, same opposite. And you divide everybody by 2. Everybody by 2. Okay, and that's the IOC. That's the interval of convergence. X. This series is this function between, for all x values between negative 1/2 and positive 1/2, not including them. When x is 1/2, there's a problem. When x is negative 1/2, there's a problem. Do you see what the problem would be if x is 1/2? Do you see what the problem would be if x is 1/2 in here? 3, 2, 1. The problem up here is that you would have 3 divided by 0. 1/2 times 2, 1. 1 minus 1, 0. Negative 1/2 is less clear, but it's not clear. It's not unclear here. When x is 1/2, what are you getting? 1 to the n. What's 1 to the n? It's always 1. So you're adding up 3 infinitely many times. That does not converge. Same thing with negative 1 to the n. You can play around with the numbers. Just know that these are not inclusive. 2 more. More complicated. Alright. This is a geometric series. Again, we want something that looks like a over 1 minus r. I think this is going to be the last time I write it because I'm getting bored of writing it. A is the top. Easy peasy. Don't hurt anybody. I can solve for r by setting it 1 minus r equals 3x. And now for the first time, some of you will really benefit from this. I don't know how you like to solve this, but we're trying to solve for r. Let's just do it the way we kept doing it before. 3x minus 1. So r equals negative 3x plus 1. Or the more common way of writing it, 1 minus 3x. This, for some reasons, are nicer. We usually like to let the positive term lead mathematical writing. I don't know. Anyway. So, h of x. A plus a times r. Weird. Plus a times r squared. A is not showing up because a is 1. Plus a times r cubed. 4 non-zero terms. And the general term. A times r to the n. Now, if you were thinking about doing something with that n right here, like distributing it, you are crazy. That is bad. Kill that virus on your hard drive. I don't know. Maybe saying kill will get me blocked by the school filter. We'll see. Anyway, that's it. So what is this equal to in sigma notation? N equals 0 to infinity, A, 1, R to the N. That's it. Interval of convergence. I want R to be less than 1. And I'm not even kidding. I'm pretty sure this is the one you would struggle with the most. I'll make this 1 with a flag. 1 minus 3x less than 1, bigger than negative 1. When I did this with BC 2 years ago, people freaked out. They haven't seen this in so long. Subtract 1 from all three sides. Negative 2, not 0. That one's 0. I'm gonna shrink. Okay. And now I have to divide everybody by a negative. And I hope to all that is good and holy, to the calculus gods themselves, that you know when we divide by a negative, we have to flip the inequality. Negative to negative makes it positive. Flip. Flip. And that's the interval of convergence. It's okay to write it like that. If it hurts your brain to look at it that way, we can always rewrite it in the nice way. That's the interval of convergence. Okay. Using the power series from example 1, let's make a new power series for f of x squared. This is going to be power series by substitution. So I look at this. The key thing, I'll just write it down over here, was that f of x in the interval of convergence was 1 minus x. Let's write out the function form of it also. 1 over 1 plus x. 1 minus x plus x squared minus x cubed plus ... plus negative 1 to the n x to the n. So now, children, ladies and gentlemen, boys and girls, young adults all, what does this notation mean? A lot of people still struggle with this long after pre-cal. This says take f, and everywhere you see an x, replace that x with an x squared. There's only one x down here. So this is the function I'm finding a power series for, but I'm not going to do all that work again. What am I going to do? I'm going to take x, and everywhere I see x, I'm going to replace it with x squared. I see an x, I replace it with x squared, squared. The 1 doesn't get replaced. I don't know why people struggle with that. I replace it with a square. I keep the exponents too, okay? Like that's at 1. Forget the ... I gotta take points off. First 4 non-zero terms and the general term. X squared to the n plus ... Let's simplify. Obvious. Power to a power, you multiply the powers. Power to a power, I multiply the powers. I can't tell you how many of my students write x to the 8th. This is x to the 6th. And again, we would simplify this x to the 2n. Knowing your exponent rules will be surprisingly helpful because of stuff like this. Example 5. Using the power series from example 2, let's make a new series for g of root x. So let's start by looking at what g of x is. Oh, it's that ugly thing? I don't want to even bother writing that. Let's just write this. Or, sorry, this. Three plus 6 root x. Oh no, I'm sorry. I got too excited. 6x plus 12x squared plus 24x cubed plus dot 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 plus 3 times 2x to the n plus dot dot dot. First 4 terms and the general term. First 4 non-zero terms and the general term. So what does g of root x mean? It means everywhere you see an x, replace it with root x. No x. 6 root x. If you want to simplify in your head, go ahead. But I'm going to write it out because, frankly, I don't trust myself. And also, frankly, this would be fine on the AP test. To root x to the n. So just simplify it just to make sure if you were simplifying it in your head like bad boys and girls. What's that? It's x to the 3/2 power. X root x would also be acceptable. Okay. I'll write this out just to, I don't know, be pedantic. Do you know what pedantic means? Pause the video and look it up. And over to, again, this is much more preferable for any number of reasons. Okay? General, don't simplify. You guys might mess that up. You might mess that up. Probably not that. Definitely that. Okay. So that was power series by substitution. Going from an old power series I know, and why would you know a power series? Well, it's about to get heavy. Trust me. Unit 7.5 and 7.6. You're going to be required to memorize 4 of them. Anyway. Maybe even 5 if you count the traditional one that we did. And that's substitution, going from one series that you know to another. Hey guys, we can also differentiate power series. Another reason we like using polynomials is because polynomials only have the power rule. How would you differentiate this? You would have to use the power rule and the chain rule, something that strikes fear into your hearts. However, to the Calculus BC student, to the Calculus 2 student, he or she knows that this is this series. A over 1 minus r. I have it memorized. You need to memorize that one too. That's the 5th one. This standard thing is really important. Okay? So then I could take its derivative. Derivative of 1, 0. Derivative of x, 1. Derivative of x squared, 2x. Derivative of x cubed, 3x squared. What was right here? Some of you may have an easy time picturing. Some of you may have a hard time picturing. It was x to the 4th. Remember, I need 4 non-zero terms for x cubed. You may have been able to picture that without writing it. You may see the pattern here. How do I differentiate this? Many students struggle with this, but this is just the power rule still. You bring down the power, and then it's x to the original power minus 1. That's it. There's the power series for f prime of x. Good? It's not that bad. Trust me. Now, the most exciting example. Oh, I can't wait. So that's a power series. Let's differentiate J prime. Let's find J prime. Let's differentiate J. 0. 1. Bring down the power. Bring down the power. Subtract 1 from the power. Bring down the power. Subtract 1 from the power. I'm going to write 2 more just to help you with the last example. That's n minus 1, that's y. And then this next one would have had a power of n plus 1. And that would have been over n plus 1 factorial. Now I'm going to write that for a very peculiar reason. Let's simplify this. And if this confuses you, you need to go back to the first example in 7-2. 1 plus, what's 2 over 2 factorial? 2 factorial is 2. 3 over 3 factorial. 3 over 3 factorial is not nothing like that one was. It's x squared. 3 with 3 factorial, I'll write it down here, equals 3 over 3 times 2 times 1, 1 over 2 factorial. 4 over 4 factorial. Again, it's not 1. It's not 4 either, sorry. It's 3 factorial. You need to understand this. You need to understand how factorials cancel. I can give you a million examples like this, or sorry, I will in the homework. Plus, dot, 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 what's happening over here? N over n factorial. It's n minus 1 factorial. The n cancels out, but then all the rest of the factorial is still intact. N plus 1 over n plus 1 factorial. It's n factorial. And what do you notice? What strange thing do we notice? It's that what I have written in green here is this. They are the same. So, a strange fact. J prime of x equals j of x. Gasp. Can you identify what j is? I think this is on yours. I'll write out who is j of x. Which function is j of x? Which function is its own derivative? Which function is its own derivative? And when you plug in 0, this is a key thing. Watch, when I plug in 0, 1 plus 0 squared plus 0 cubed, j of 0 is 1. There's only one function that has the point 0, 1, and who's its own derivative. If you said or thought j of x is e to the x, you are right. So that's e to the x. And we're going to get to know him really well in that form. Because that version of e to the x is very, very nice for a number of reasons. Start memorizing it now. That's one of the 4 elementary series you'll need to know. Shocking. Shocking, I say. All right. Number 8. 8, 9, and 10 are the coup de grace here. A lot of people don't like integrating both sides. This is example 1. Look back. 1 over 1 plus t is this. So now if I wanted to integrate both sides, I could. You can always get new power series by integrating old power series. On this side, in this corner, what's the integral? The derivative of the whole bottom is 1. That's on the top. When it's in that relationship, derivative over the original, it's a natural log, guys. Natural log 1 plus t evaluated from 0 to x. Okay? Just going to leave that side like that for now. On this side, how do I integrate infinitely many things? Just one step at a time. The integral of 1, t. The integral of t, t squared over 2. The integral of t squared, t cubed over 3. The integral of t cubed, negative t cubed. T to the 4th over 4. I add 1 to the power, I divide by the new power. And that's what will get us all the way over here. What's this integral with respect to t? Well, this is just some number. N is just some number at this point. So that gets left alone. It's still negative 1 to the n. How do I integrate t to the n? I add 1 to the power, and I divide by the new power. Don't worry about plus c. Don't worry about plus c. It's a definite integral. Okay. On this side, a lot of people got worried in class. So it's absolute value 1 plus x minus natural log. I'll do it. It sounded like a threat. Okay. Now, I don't really want to have to write all of this out, but I will. I'm just plugging in x everywhere I see t. Easy peasy. A lot of students struggled with this on their test. They struggled with the idea, oh, I have to replace t with x. Yep. Oh, this says t. Oh, that says x. Something's happening. Okay. It's a really weird example, but it's a really important example because it's giving you your second elementary series. Hint. Natural log of 1 plus 0 is 0. Oh, sorry. Minus. When I plug in 0 over here, 0 minus 0 squared plus 0 cubed. Okay? I'm subtracting 0 from the end. So there's nothing else to worry about. So what we've shown, children, let's think about the interval of convergence. What was the IOC over here? If you look back at example 1, I don't know what I'm doing down there. If you look back at example 1, the interval of convergence here was x is between -1 and +1. So if x is strictly greater than -1, this is always positive. If x is strictly less than 1, it's always positive. The inside's always positive. Okay, natural log's not, but. So, I'm going to wrap this up. I get rid of the absolute value because the inside is always positive. That was 0. Natural log of 1 is 0. And now I have an elementary series for natural log of 1 plus x. Some students teach their children to memorize it that way. We're going to go a little harder. We're going to memorize the natural log version, not that 1 plus the natural log version. Even though this is in some sense more natural. Okay? Plus ... always. So now I found a new series for natural log. Use this result to write a new series for natural log x. So the idea is, what would I be replacing the inside with? Okay. I would say natural log 1 plus x minus 1 Does everyone see how that's true? Think about it. Okay. The idea is that I know this side, it's substitution. Everywhere I see x, I'm going to replace it with x minus 1. Right. So I'll just write, okay, so natural log, I don't mind writing it again. We cool. Ooh, it's alternating. That's going to be an important idea. The nth term is something like you can still write it as n plus 1, and n. It's up to you. Like, that's just the next term. Don't get too bogged down over here. The key thing is that you understand the first 4 terms. That's what I want you to focus on now. So now, everywhere I see x, I'm going to replace it with x minus 1. So, natural log x equals, everywhere I see x, I replace it with x minus 1. X minus 1. X minus 1 squared over 2. Oh, that was a bad fraction bar, sorry. X minus 1 cubed over 3. Oh no! That should have been negative. Ah, I hate this so much. I hate natural log. It's the worst. So, there we go. That one. I knew it should be alternating though. That's where my skills are at. My skills are on point. On fleek. I know that's not a thing anymore. I'm not trying to be cool. I'm trying to be lame. Just to make you laugh while you're watching this calculus video at 1 a.m. You know who you are. Matchy matchy, off by 1. So you can write this last one. Matchy matchy, off by 1. Plus dot dot dot. And that's natural log x, ladies and gentlemen. The most awful one for sure. Alright. So now we're going to put these things together. Write a power series for g of x equals this. Well, like I just said, and you should have it right on your paper, natural log x equals this. See how much I care about you? I'm writing it over and over again. You should write it over and over again too, because honestly, it will make you remember it much, much better. Almost wrote it not. Oh, I can't believe it. It alternates, Mr. Leven. You need to write the fact that it alternates. Move it over so I can make the dot, dot, dot. I'm not going to write both terms now. Negative 1 to the n minus 1, off by 1. That's why it's so stupid. Nobody likes you, natural log. Matchy, matchy. So the idea is, well, if I take this side and multiply it by x squared, what would happen over here? I would multiply each and every term by x squared. Right? I'm just kind of distributing it out. It's that easy. So I hope you're coming away from this lesson maybe with a modicum of confusion. I don't really hope for that. But an idea that, well, it's not so bad. There's some weird tricks with the integration. But everything else, the reason we're doing this is because differentiating and integrating polynomials is easy for you guys. Times x squared times x minus 1 to the n. That's a square. All over n. Plus dot dot dot. So differentiating this would be a nightmare, but the idea is that you're never ever going to be asked to differentiate this. You're only ever going to be asked to integrate nice things and differentiate nice things. The homework will have you integrating arctan, or finding a power series for arctan. It's not that bad. Just go slowly. I cannot emphasize enough. My parents made fun of me this last night. You will fail the BC test if you're not doing these assignments. So if you're watching this video at 1 a.m. on May 9th, you're not going to do well. And that's the first time you're watching. If you're watching a review, that's different. Make sure you do the assignments. Do the assignments over and over again. Come and ask questions. If you are doing the assignments, I really do appreciate your hard work. Anyway, I also appreciate the fact that you're watching this video at all. So, watching math videos on your free time, that's pretty interesting. I'm pretty proud of you guys. Alright, so keep up the hard work. You have a great day, great night, whatever. And I'll talk to you soon. Bye-bye.